Hi everyone, can you hear me? So in this session, we will see file systems. This file systems is, one of the, I can say, very easy topic. Not just easy, it is a very easy topic, and you can easily get full marks in this particular topic. So Gate has been asking this topic since in every 2 3 years they ask this. Very simple question from this topic. So we will see that how to solve questions from this topic and what is this topic. So as I'm saying here that we will see everything from scratch. Okay. So we will see everything from scratch and with all gate PYQs, right? So let's just get started. So see, if you do not know anything regarding the file system, then don't worry about it. We will see everything from scratch and that too with all gate PYQs. Okay. So two things are important here. Great. So let's just get started, right? So what is file? So as you might guess, as you know, as you probably already know, that file is some data in some format, right? So data in some format. So what are the formats possible? So there are like many formats possible: .bak, .c, .gif, .hlp, or MP3, JPG. Okay, .o, .pdf, .ps. So there are many formats possible. So this screenshot I've taken from 10mm. Okay, so there are many formats possible, and a file is basically some data in one of this format. Okay, and what are the operations you can do on the files? You can create, you can rename, you can open, you can read, you can write, and so on. Okay, great. Now, what is file system? See, we know what is file, but what is file system? It is some systematic way that provides a way to store files. Okay. So what does this mean? I will just very clearly tell you that it is one systematic way to store the files. Okay. Basically whenever you have multiple files, okay, let's suppose this is file 1, this is file 2. Okay, suppose you have many files. Okay, file 100 or something, right? Suppose you have many files, and whenever you have multiple files, in that case, okay, so in that case, you need to know that how to store these files, right? How to store all of these files in your disk. So you want to store, how to store, right? You can directly store, or basically there should be some way to store, right? So which means that whatever is the disk. So let's suppose this is the disk. So whether you will be keeping this file one here, and if you're keeping it here, then for example, let's suppose this is your disk. Okay, then let's suppose file 1 is here. Then should you be keeping this file 1 entirely at one place, or can you divide this in multiple places? Okay, and if you're keeping in one place, then what is the structure, in the sense that how we will be retrieving this file, right? How we will get this file again? So basically file systems tell you everything. Provides a way to store, provides a way to name the file, provides a way to store the metadata of the file. So like there are many things that file system provides. So for example, it provides a way to store, and then way to retrieve. So you can't randomly just store anywhere, because you should be knowing where you have stored, right? Let's suppose file 2 is stored here, right? So you should know where these files are stored. You should know where these files are stored, right? So you should definitely know this. Now, basically the thing here is that the file system tells you everything about the organization of the files. Okay, so we will get to understand the file system very clearly here. Now, what is the objective of this lecture? Objective, or not only lecture, but objective of the file system is basically to provide a file system structure, allocation method, which means that how to store. Allocation means store. Okay, storing the files. And there is something called disk management, which deals with the disk structure, disk scheduling, and so on. So basically, the file system is kind of, I can say, it is like kind of software things that we are dealing. Okay, and disk management is kind of hardware things that we need to do. Okay, so in operating systems, you only have the file systems. Okay, this is part of, you can say, this is part of operating systems. because this is software things. Since it is hardware thing, this is part of computer organization, right? So we have already taught this. I think in our Go classes course, these lectures like disk management lectures are in DBMS. Okay, in Go classes basically, Deepak sir has taken in DBMS, right? Okay. So, so I hope you understood that basically the file system is part of operating system, but disk management, which means that what are the sectors and how disk scheduling and these things are basically hardware part. So our objective is this. This is our objective. Okay. So file systems is, you can say, our objective. Understood? Okay. So let's just design some file system. That how to design the file system. So basically, your disk will look like this. This is your disk. Let me just tell you that your disk has something called as sectors or blocks. Okay. So basically, you will be writing everything in the sector or the block. So in disk, in disk, you have something like this, and then you don't have the bytes here. Okay. You will say that disk is divided into the blocks. Disk is divided, okay, not bytes, which means, or sectors. Okay, blocks and sectors both are same, which means that if you want to read something from the disk, then you have to take the entire sector. Okay, you can't just read one byte only, you have to take the entire sector. Okay, and to the main memory. Basically you have disk here. For example, you have main memory here and you have disk here, right? Now your disk is divided into the sectors, something like this. Then if you want to read even, let's suppose, one byte from the disk, right? Then you have to bring the whole complete, you have to bring this complete sector to the main memory. Okay, so this is called reading. Okay, read from disk. This is called read from disk. Is this fine to everyone? So basically, disk is divided into the sectors, and you have to read the complete sector. Okay. So if I just ask you very simple question, let me just ask you a very simple question, that what is the smallest addressable piece of data in disk drive? What is the smallest addressable piece of data? It is basically sector or block. You can say smallest is block. Okay. You have to read one block only. Is this understood to everyone? So basically, this sector or block, right? Now, now, if we want to design a file system, then as we know that disk offer a huge amount of storage, right? The problem is that what to do with this storage. So we have huge amount of storage, and then we want to make use of this storage. Okay. So let's just see that how we can make use of this storage. Our disk is basically separated into the chunks called sectors. So basically, we have separated this into the sectors. Okay, great. Now, this complete disk is like, as we have divided this into the sectors, so you can view this complete disk as a array, as an array. Okay, I mean this is basically some rotational disk or something, but still you can view as an array only. Okay, for example, you can view disk like this. Okay, this is view of disk. Is this okay to everyone? So basically you can view disk as an array. Disk can be viewed as an array of blocks. Okay, and then in the disk we store obviously files, right? So suppose this is the disk that we have. Then obviously ultimate aim is to store files, right? So here in this disk, ultimate aim is to store files. So most of the sectors, okay, so most of the sectors are occupied with the files data. But we need to have few metadata also. Okay, metadata means some data which is useful for the file, which means, for example, let's suppose the file 1 is stored here, right? So I should be knowing that file 1 is stored at the sector number 4. Okay, so metadata means like data related to some file. Okay, data related to file. For example, let me just show you. See, metadata looks like this. Sorry. Okay. So metadata looks like this. So which means you have something like this. I mean, you also have to store things about the file. For example, the name of the file. Okay. See here that you might already see if you are using your computer, then you can see the properties of the file, right? So properties of the file are called metadata. Okay. So this could be that, okay, what is the name of the file, what is the size it is taking, and so on, what is the extension of the file. So properties of the file is called metadata. Okay. So we also need to store the metadata and obviously the files data. So you can say that most of the okay you can say that most of sectors has files have files, but few starting sectors or few starting blocks have some metadata. Okay. So there are some specific names of the metadata. I mean, there is something called boot block, super block, inodes. Like, you don't need to know these names, but I'm just telling you that few starting, okay, few, let's suppose here, I think in this case, out of all, maybe they have taken files metadata, have taken, I think, three or something, right? Okay, I think 1024. Okay, so files metadata have taken 1024 blocks or something. Okay, so it depends obviously on the file system, but yes, few blocks are reserved for the, generally I think there are like not more than, I mean, it will obviously depend on the file structure, so let's not comment on this, but few starting blocks you can say are reserved for the metadata, right? Okay. Now, as you can see that this is the metadata. Okay, we will come to this inode, because this is one thing that we need to know. Otherwise, like, this is the metadata, right? Okay. So let's design a file system. So as you know that we have a huge disk which is something like this, which is looking something like this, and we want to know that how to design a file system. So what is a file system, by the way? File system is basically a way to provide. What is the file system? Well, file system is a way to provide, that how to store files in the disk. Okay, I mean, you should be storing file one here, or where, or how to store the metadata, everything, right? So file system is a way to provide the proper structure to store the files. So popular file system idea is that store information about each file in addition to file contents. For example, for example, uh, basically, this is like, we will be either calling it payload or metadata, doesn't matter. So basically, popular file system says that we will be having the file, each file in addition to its content. Okay, we will be storing the information about each file, which is called metadata, plus file itself, right? File itself, obviously, like, so great, we have the sectors and we have the metadata. How do we allocate our space for the files? So that is the question that we need to ask, that we need to answer. That we have, like, file is basically consisting of metadata, and there is a file, and we want to store these things, right, these things to our disk. Then how to store these things to our disk? This is the question that we want to answer. Understood? So now let's just see that how we can answer such question. Okay. Now, see, we want to store file and metadata to the disk. This is the question that we want to answer. But before that, let me just ask you that why do we need allocation strategies? I mean, that can't you just randomly put? My question is that you have files, right? So you have, let's suppose, file one, you have files. So file one, file two, right? Something like this, right? So can't you just randomly put, I mean, let's just put file one here, let's just put file two here. So the thing is that my question is that can't we just randomly put? This is my question. The answer obviously is no, right? I mean, we should not be putting it randomly. The reason is that, I mean, we should be knowing that where is the file one, where is file two, and data should not be mixed. I mean, we should be easily able to retrieve the data, and there are many other things that we need to do. We need to provide the, sometimes we need to also, we need to provide the production also, whether it is read only, write only, something like this, right? So basically, files are stored on the disk. So OS must decide how to place blocks of the file on the disk, right? I mean, basically, how to fetch the blocks efficiently, how to avoid fragmentation, mixing of the files. Like, you don't want to mix two files or something, right? So basically, the thing here is that you want to make sure that everything runs very smooth, right? You don't want to mix up the files. You don't want to, you want to fetch the blocks efficiently. Basically, where is the file one, you should be getting it immediately. It should not be taking too long to just, see that, okay, where is the file one. So good file systems will give you, better fetch and better storage, something like this, right? So basically, we definitely need some file system, or we definitely need some allocation strategies. Now let's see some popular allocation strategies. So basically, there are few common allocation methods. Let's see in the next slide. So one is called contiguous, another is linked, another is indexed. So these are the three popular systems that are basically being used even in the modern operating systems. Okay, in Windows, one version of linked, I mean one variation of linked is basically Windows is using one version of linked or something like this, right? So basically, these are the three allocation strategies. So let me sum up that what we are talking about. So we are just saying that we have our disk. Okay. So this is our disk. We want to store things in our disk, right? Things means files. So we want to store files. Now, how to store? There could be, different file systems. There could be different allocation strategies. Store means allocation, right? So how to store? One way is a contiguous allocation. Another is linked. Another is indexed. Okay. So let's just see what are these three. Let me just tell you what are these three. So by the way, we have, for the contiguous, we have one small variation which we will study called extend based. For the linked also we have one small variation. For the indexed also we have a small variation. So I can say total 3 plus 3 allocation allocation strategies allocation strategies will be there. Okay, we will see, right? So there are total, you can say, 6 allocation strategies, right? And these 6 basically depending on some key metric that, okay, we should be getting the data immediately or something like this, right? So let's just see the very first so that you get the idea. Very first is basically, you can say, very trivial. I mean, if you want to store a file, they are saying just store it contiguously. Okay, this is called contiguous allocation. If you want to store file into this disk, then store this contiguously. Okay, that's you can say this is very trivial. This is very trivial way to store files. Okay, this is extremely trivial way. Is this okay to everyone? Okay, great. So now you want to store the files on the disk. One allocation strategy you can do is that you can do contiguous allocation, which fills which file get stored contiguously on the disk. Okay, it is very easy. Another one, as I told you, there are like three, right? One is contiguous, another one is linked, another one is indexed. Okay, there are three. So contiguous I have just shown you. Now let's just see linked, and then we will see indexed. So now we are basically seeing this linked, right? Let's just see this. So file can be stored in the contiguous, we were storing directly, but in the linked we are basically storing as a linked list. Okay, as a linked list, which means that first block will be basically where, let's suppose this is a file. So obviously this file has to be divided into the blocks. Okay, so see here that you have a disk. See, you have this disk and you have file, right? So you will be dividing file also into the blocks. This is your disk and this is your file. Okay, you divide this also into the blocks. Let's suppose it needs three blocks. Okay, let's suppose file one needs three blocks. Then in contiguous, this is saying that you store this whole thing, okay, contiguously in three sectors or three blocks, right? So let's suppose these are the three blocks, one, two, three, and here the file one you are storing. In contiguous, you are storing it contiguously, right? But in linked, they are saying that you don't have to store this contiguously. Okay. What you can do, let's suppose this is the block one of file one, this is block two of file two, this is block three of file three, right? You can store this block one anywhere. Okay, doesn't matter. Let's suppose I'm storing this block one here. You can store the block two here. Okay. And then you can store block three here. I mean, anywhere. Okay. Basically, they are saying that you can store anywhere. Whenever you are at block one, we will just get to know that where is the block one. Whenever you are at block one, then you will automatically using the list, using the pointer, you will automatically get to know where is block two, and then you will automatically get to know where is block three. And then this pointer will be null. Okay, this will be null. Null means that it is not pointing to any block. Okay, is this fine to everyone? That what we are doing, we are saying that this file can be can be stored in the disk as a linked list, which means you are storing block 1 somewhere, you can store block 2 somewhere, you can store block 3 anywhere, right? And then you can link them. This strategy is called linked allocation. Okay, so in the contiguous allocation we were storing contiguously. In the linked allocation we are storing as a link, right? Now, what is the third one? Third one is indexed. See, in the link, there is a small problem that you might identify. What is the small problem that you might identify? That if you want to go to this particular block, then you have to first go here, then here, right? So this is the small problem that you have here in the linked. Okay. So that is why they are coming up with the one more solution, which is indexed. Indexed is saying that we will be having all the pointers, okay, all of these pointers at one place um, in the metadata itself. So basically, index is saying basically this metadata is called inode. Okay, inode is just metadata. Okay, I mean this is the name of metadata in case of index allocation. So it says that I will be storing, okay, all of these pointers. See, earlier these were linked, right? Earlier these were linked like this. Okay, earlier these were linked like this. Now they are saying, now they are saying what you can do, you can if you want, okay, you can store all of these pointers directly in the metadata. So if you want to go to the fifth block, let's suppose you want to go to the fifth block here. See, let me just compare this index allocation, okay, and linked allocation. See, this is the linked allocation. So can you see the clear benefit in the index allocation? This is linked, this is indexed, right? In indexed, in index, basically they say if you want to go to the fifth block, let's suppose to the fourth block, then 1 2 3 4, you can directly go here, okay, to this entry, and then you can directly go to the fourth block, right? Very immediately you can go to the fourth block here or any block. But here if you want to go if you want to go to fourth block, then 1 2 3 and then 4, you have to do sequential access. Okay, you have to do sequential access. Is this fine to everyone? So obviously this index is having some advantage. So let me basically tell you that we have seen three strategies. One is contiguous, another one is linked, another one is indexed. Okay, so these are the three only in the syllabus. I have just given you a small brief about these three strategy. Now we will see questions on this, and we will solve all the gate questions. So as a theory, it doesn't have much theory. Okay, the file system, the good part about the file system is that it doesn't have very much theory. Okay, you can say that the almost, I mean, we just need to obviously study little more theory, but almost all the theory is done. Okay, so this is contiguous. Let me know if this is fine to everyone. In contiguous, we are storing contiguously, right? In contiguous, we are storing contiguously. In linked, we are basically linking each file, which means let's suppose this is a block of each file. Let's suppose if we are talking about the file one, okay. Let's suppose this is file one. Here also I'm storing file one. Let's suppose here also I'm storing file one. So file one, let's suppose has multiple blocks, one, two, three, four. Okay, this is a block one and block two. So block one can be stored anywhere, block two can be stored anywhere. I just need to link them, right? So these are the three strategies. Let me know if it is fine that what are these three things are doing. Okay, what are these three methods to store the file on the disk? Okay, so you can say these are the three main methods to store file on the disk, and almost all theory is done. But little more theory we will see, and then we will practice questions, right? So in the file system there is not much theory. So this is, you can say, three popular ways to store files. Understood? Now, as I told you that these are the three ways, right? But these three ways has small variations also. Okay, so that makes it six ways. Okay, so basically these three ways are okay. We will see small variations of these three ways, and then totally we will see total six ways, right? Is this understood to everyone? So now let's just see uh, these variations also. Okay, so one is variation to contiguous, one another is variation to linked, another is variation to indexed. But before I go to the variations, I want to make sure that these three are clear to everyone. See, you don't have to, obviously, initially you have to remember, but ultimately it will be, making sense with the names. I mean, contiguous means you are storing contiguous, linked means you are storing as a linked list, index means all, like we are basically storing all the pointers in the metadata itself. Metadata name here is inode, okay? Index node. So basically, this is the metadata. I mean, everything has the metadata. It's not like that only index has metadata. Here, this is metadata. I mean, the first pointer to the first block is metadata. Okay, we need to know where is what is the pointer to the first block. This is the metadata. Here the metadata will be start and end. Okay, here the metadata must contain start, where it is starting, or length or end. Okay, doesn't matter. So it can contain a start. So what is the starting block and what is the length of the file? How many blocks it is taking basically. Okay, is this fine to everyone? Great. So so now let's just see their variations. Contiguous is okay, but let's just see this contiguous little more, and followed by the variation of the contiguous. So the most straightforward way to handle this to store the files in the contiguous ways. Okay, so suppose you want to store 400 bytes, then you can store directly here. Let's suppose each of the sector is 512 bytes. Okay, suppose the block size is 512 bytes. So if we are storing 400 bytes, then few bytes, which are like, you can say, 112 bytes empty, will be empty. I mean, within this block, 112 bytes will be empty. Okay. Is this understood to everyone? Now, suppose we want to store 700 bytes. Okay. Now, next, suppose we want to store 700 bytes. Then what we will do? We will allocate, some other sectors. So let's suppose 500 and then two more 100, right? 200 more. Okay. 200 more. So basically now we are storing 700 bytes of the file, another file. So file B must start the new sector even though there is a leftover space in sector 0. I mean, it's not like that I can store some part here. Okay, it's not like that. I mean, one block must be containing only one file. It's not like that file B can be stored here or something. Okay. So that's how we store, as we know. I mean, this is a contiguous allocation. right? So in the contiguous, files are stored contiguously. So you can, as a metadata, this is the metadata, right? This is metadata. As metadata, you can basically store what is the starting address and what is the length. This is the file B where you are storing file B. Suppose you are storing these two files, and now suppose you want to store file C, which needs two sector. Can you store file C, which needs two sectors? Okay. Can you store file C, okay, which needs, tell me. See, since it is contiguous, so that is the reason you can't store file C, right? I mean, even though there is some space, still you can't store file C. This is called external fragmentation, in the sense that you are having, externally, basically these blocks are basically empty. Okay, I mean, fragmentation means wastage. Okay, this is called external fragmentation. Fragmentation basically means wastage, kind of. Okay, I mean, kind of, you can think like this. So which means they are saying that even though you have three empty sectors, still you can't store file C, which just need two sectors. Why? Because of the method you are using. Okay, because of the method we are using. This is called external fragmentation, right? So what is the advantage? This is very easy, straightforward to implement. What is the disadvantage? There's the external fragmentation and difficult to grow files. For example, now file A wants to grow, let's suppose, two more sectors. Then it is difficult, right? I mean, you have to shift this here and there and so on, right? So basically, it is difficult to grow files and easy to implement, but it is having the large external fragmentation. See, the thing here is that you don't have to remember anything. You just need to know what is contiguous. Okay. Once you know what is contiguous, you can tell that okay, it is easy to implement. It might be having the external fragmentation. The internal is anyway there. Internal actually is almost there in all the methods, because you can't do anything for the internal fragmentation, right? I mean, if the file is not taking the whole sector, then what you can do, right? This is called internal fragmentation whenever you are wasting the space within a block. But if you're wasting the entire block for some reason, okay, I mean, you have to waste the entire block for some reason. That's called external fragmentation. So we will be interested in the external fragmentation only, because internal we anyway can't control, and it is just for the last block. Okay, just for the last block, little bit of space will be there. This is okay. I mean, this is manageable. Okay. So what we can do here in this scenario, what we can do such that we can store file C also. Can we allow, okay, the variation of the contiguous says that we will be allowing this file C to get stored at multiple locations. Okay, so we will be allowing this file C to get stored at multiple location, and which is called extent based. So this is the variation to contiguous that we will see, and this variation will tell you that how to allow one file to store at multiple location and need not to be exactly contiguous. So let's just see, this is called extent based. Basically, it is saying that multiple contiguous regions per file. So each region is called extent. Let me just tell you what does this mean. See, they are saying that you are having, let's suppose this is the disk, right? Then they are saying that what you can do, you can store, your file. Let's suppose this is file, some file. You can store the file here, here, two contiguous blocks here, and let's suppose three contiguous blocks here. This combinedly is file one only. Okay, this is file one only. So they are saying that you can store at multiple contiguous locations, and each of this region is called extent. Okay, they are calling it extent, right? So let's do one thing. Let's solve some question, and then you will get to understand this very easily. That what do I mean by that? So what are the pros and cons? It is okay. We will solve first questions, and then you will get to understand that what do I mean to say. So let's solve this question. A file is stored using three extents, which means it is taking three places. Okay. So a file is taking three contiguous regions differently. Okay. Suppose suppose somewhere it is taking somewhere here. A file is taking somewhere here, another here, another here. Okay. Doesn't matter. So basically, this is just a single file, but these are the three extents. Let me call this E1. Let me call this E2. Let me call this E3. This is a single file. Extent 1 start from 40 and length is 5. Everything here, notice here is that everything here is in the terms of block. So length 5 means 5 blocks. Okay. So it is taking 5 blocks. And extent 2 is taking 3 blocks. Extent 3 is taking 4 blocks. So how many total blocks this the file will take? Tell me. You just need to sum this up, right? So this is 5 plus 3, 8 plus 4, 12, right? So C is the correct answer here. C is the answer. So how many total extents this will be taking? So total blocks it will be taking 12. Okay. So easy question, but it is just there to make you understand the extents. Okay. So C is the answer. Have you understood this question? So you are taking three extents. This is a variation of contiguous. Okay. Now, let's solve this question. What they are saying, consider a file stored using a contiguous allocation starting at 50. The directory entry is basically metadata only. So directory entry we will be using again and again. This is only metadata. Okay. I mean, we call metadata is directory entry. I mean, sometimes we call it inode. Okay. I will just tell you in case of indexed allocation, we call it inode, but in other cases we also call it directory entry. Okay. Or file control block or something. Okay. It will be clear, like these are just one two terms that will keep on coming as in metadata. So metadata, directory entry is basically metadata. So directory entry for these files store start and length. Okay. So basically they are saying that starting block is 50, so you are starting at 50, block number 50, and length is 5, which means 1, 2, 3, 4, and 5. Okay. So 51, 52, 53, 1, 2, 3, 4, and 5. So 54. So what are the block numbers occupied? 50 to 54. So this is an easy question. You can say that A is correct answer here. Okay. A is correct answer here. Understood? So this is contiguous. This is not extent. In extent, we used multiple contiguous regions, but here we are using just one contiguous region. Just a small change. Okay, just a small change. This is extent. Is this fine to everyone? Great. Now let's see linked. Okay. We little bit we know about the linked, but we will see both of these variations. One is linked, and the variation of linked, which is very very popular. Okay, so I can say this is extremely popular. This is very popular. Even Windows use this variation. Okay, this is very popular variation. Gate has asked, I think 2 3 questions from this variation. Okay. So we will be solving gate questions, don't worry. But yeah, this is very popular. Now let's see linked. So we already know what is linked, right? This is how the link is behaving. Now, one other variation of the linked is called FAT, which is file allocation table. Okay. What does this variation says? It says that in the linked, okay, in linked, the problem here is that we are going, we are basically chasing the pointers. Okay. So So here in the linked, basically we are the sequential access is tough. You can say, right. This is linked and sequential access is tough. Fat is very very smart idea, which is just like linked. It doesn't do anything to the linked. This is as it is, but it maintain. Okay, fat maintain one extra table. okay, called called fat only, right? File allocation table. I mean, the structure is same, okay, but it is basically maintaining one extra table, file allocation table. For, I mean, one single fat for all the files, okay, okay, just one fat for all files, for all files. So how does it behave? Let me just tell you. Okay, basically it says that what you do, you have your disk, right? In the disk, you, assuming that you are using the linked, whenever you are using the linked, then only you can extend it, or you can basically have the variation of the fat. I mean, it is useful only for the linked. So suppose this is the disk that you have. Okay, yes, you might have heard about the fat whenever you format, or whenever you do things in your hard drive. How many of you, seen fat on your computer screen sometimes? Okay, this is fat 32 or something like this. Okay, how many of you have seen fat? You might have seen this, right? So suppose in this disk, file one is stored like this. I mean, one block is stored here, and then it is saying that another block is stored, let's suppose, here. Okay, and then another block is, let's suppose, stored here. This is suppose file one. Okay, this is file one storage. Okay, similarly, file two might have been stored like this. This is, let's suppose, file two. Okay, so this is file two. So now, fat table says that I will be maintaining how many blocks it has. Let's suppose 2 power m blocks or something. Okay, let's suppose 2 power m blocks it has. Okay, then for every block there is one entry. There is just one table for entire disk. Okay, just one table for entire disk, having 2 power m entries. I mean, number of blocks. Okay, if number of blocks, let's suppose, let me simplify this, not 2 power m. Let me just take n blocks. Okay, suppose you have n blocks, right? Then how many entries it will be having? For each block there is one entry. Okay, for each block there is one entry. So this is fat table, which is having n entries, right? Now okay, so one of the student is saying that when I was kid, in the comments he's saying, when I was kid, I used to find it funny that how does my hard disk can be fat. Fat means like fatty, right? Okay, so it's the full form is file allocation table. Okay, so suppose this is block number 0, this is block number 1, this is block 2, 3, 4, 5, 6, 7, 8, 9, something like this, right? And then 10 and so on. So every entry will tell something. So here 0, 1, 2, 3, 4, 5, 6, 7, 8, and let's suppose this is 9, and then even more, right? Okay. See here that 1 is linked to 5, right? So in front of 1 you will be writing 5. Okay, here you will be writing 5, just 5. What does this mean? That whenever you are coming to 1, okay, I mean, where to go next? This is just maintaining next block, just maintaining next block. That where to go next? Here, if you are at 1, then you go to 5. If you are at 5, can you tell me where to go next? At 6, right? So if you're at 5, go to 6. If you're at 6, then you don't have to go anywhere, so you can store null. Okay, or some people call it end of file, EOF, which is same as null. Okay, which is, I mean, this is null only. If you're at 3 then where to go? Then you will go into 7. At in front of 3 you write 7. In front of 3 you write 7. Okay, if you're at 7, then you will go into 9. Okay, if you're at 7, then you will go into 9. If you're at 7, you will go to 9. So basically, this will just store the next block. So you can say fat stores all pointers. The thing here is that it is still linked. Okay, it is the way we are storing it is still in the linked list way, but I am bringing all of these pointers here. Okay, so I just need to know the start pointer. Obviously I will be getting the start pointer from the metadata. I mean, here also I need to know the start pointer. Okay, so I just need to know the start pointer. Let's suppose I want to access the file 2. Okay, see here, let me just give you the example. See, these are the start pointers, which directory or the metadata will be containing. Okay, these are the start pointers. Now suppose I ask you that how to traverse file A and how to traverse file B. For the file A, what will you say? That start pointer is 6. Now first block is 6. Okay, so the first block is 6. I mean, file A is here. This is my file A. This is file A, right? And the next block, now here, from here I will be going to 4. Next block is 4. From 4 I will be going to 3. Next block is 3. And then from 3, this is null or EOF. EOF means end of file. I mean, this is null. So that is how I will be basically storing my pointers. I mean, all of the pointers I am bringing at one place. Okay, and start pointers or starting block you will be getting from the metadata. Directory means metadata. Okay, so start pointers you will be getting from the metadata, but I mean, remaining job you can do with the fat. Understood? Similarly, for file 2 or file B, you will be starting at 2. So file B, you will be starting at 2, right? And then you go to 1, and 1, from 1 there is nowhere, right? So how many blocks file B is taking? File B is taking 2 blocks and file A is taking 3 blocks. So that's how you can traverse. Is this okay to everyone? Let me know. See here, obviously you don't have to. I mean, don't have to store the pointers here. You don't have to store the pointers here. Why will you be storing the pointers again and again, right? Obviously you don't have to store the pointers here. But the fact is saying that I'm bringing all of these pointers at one place. Okay, so it is just a way of saying that I'm bringing all of these pointers at one place. So then you no longer have to store the pointers here, right? So all of these pointers, okay, for all the files, not for just one file, for all the files I'm bringing at the one place. Is this okay? Now, see, we are see here, we are still doing the pointer chasing, right? I mean, we are still basically going to let's suppose 6, and say from 6 we are going to 4, from 4 we are going to 3, and then we are still doing the pointer chasing, right? So what is the benefit over this linked list? What is the benefit? Can you guess? We are still doing the pointer chasing, then what is the benefit over linked? See, in linked, the pointers are basically within the disk, right? I mean, within the block. So you will get to understand in a while. Basically, let's suppose. Let me ask you one question. Probably you can answer this question now only. Let me ask you one question. See, suppose suppose I want to go to, or I want to read, let's suppose this. Okay, I want to read this block. So basically, I have to first read this pointer, then read this pointer, then read this pointer, and then I can, okay, then only I can read this block, right? Now to read any pointer or anything from this, Okay, to read anything from this, since this is in the disk, you have to bring this in the main memory. Okay, so you have to bring this in the main memory, then read this pointer, then you get to know, okay, where to go next. Okay, here you want to go next, then you bring this also in the main memory. Okay, then you go get to know, okay, what is the pointer, then you bring this also in the main memory, and then you get to know what is the pointer, and then you get to get the access of this. So how many total reads are required, or you can say total disk access? Three disk access, I mean three reads are required to read these three blocks. Three read, right? To read these three blocks I have to read, and ultimately I have to read this obviously, then one more read. Okay, so total four reads are required here. See, you will get to understand in a while. Don't worry if there is any problem here. What I'm saying, that this fat is having advantage. The advantage is that now you just understand the advantage. Okay, the advantage is that in fat, let's suppose, see, this is fat. Now suppose I want to do the similar thing. Okay, suppose the scenario is fat. Okay, I mean suppose this is not linked list. Okay, suppose the scenario is basically fat, which means you have a single table. Okay, where this is the fat table. So what you can do, you can bring this fat table, okay, this fat table to main memory. This is main memory. Okay, bring complete or entire fat table to main memory. Now also you have to do the pointer chasing, but since this fat table is in the main memory, this is fat table. Okay, now you have to do the pointer chasing within the main memory. I mean, you don't have to take this, okay, read it, then take this, read it. You don't have to do again and again. Yes, yes. So here total one read for fat. Okay, for fat is required, I mean one disk access. So here if I just ask you total disk, total read access, read disk access. Okay, so one for fat plus one for desired block. Let's suppose you get the pointer of this. Okay, you can get it from the fat, you can do the pointer chasing, and then you can go get the address of this, right? And then obviously you have to bring this also, right? To bring this you need one more read, okay, for the desired block. So it is always two. It is always two. Is this okay to everyone, that what is happening here? Okay, in case of linked list, you have to basically bring each of the block individually into the main memory, and then then only you will be getting the pointers. See, there is no other way to read anything from this other than bringing this whole thing to the main memory, and this is requiring one read access. Okay, so one read access because I want to read this, one read access because I want to read this, one another read access I want to read this, and then read access because maybe I want to read some data from here. Okay, so I anyway need four here. Okay, it could be thousand, it will depend on that which block I want to read. Okay, but here interestingly, here it is always two. Okay, one for fat, I'm assuming that this fat you can bring just at one axis. So one for fat and another for the actual block. So what do I mean by read? See see you have your disk. Okay, this is your disk, these are the blocks. Okay, it doesn't matter what you want to access from this disk, right? So let me just make it very very clear that what are the read and write mean. Okay, see, this is your disk, this is, let's suppose, your main memory. Okay, now suppose this is block 0, this is block 1, like this, right? Now suppose you want to read anything from this block. In that case, you have to bring the complete block to main memory. This is called read access. This will take one read access. Okay. Now you have, let's suppose, brought it, okay, completely to the main memory. Let's suppose this is here. Okay. This is the block 3, right? Now from block 3, let's suppose you get to know that okay, you want to go to somewhere else. I mean, there is some pointer, and then you go to that thing. Then you want to read something from here, let's suppose. Then you bring this block also. This is another read. Okay, this is another read. You have to, each time whenever you want to basically read anything, or you want to know anything from this block, you have to bring first in the main memory. This is another read access. Okay, let's suppose you are bringing some other block also. Okay, let's suppose block number anything. Okay, let's suppose this is block number 4 5, or let's suppose this is block number 5. Okay, suppose this is block number 5. So this is block 5 you are bringing, right? Now suppose you are doing some change in block 5. Okay, some change you do block 5, in the block 5, and then you want to restore this also. Okay, here, because some change you have done. In case if you have do some change, then you obviously want to store also, right? This is called write access. Okay, so basically you're reading, if you want to read anything from here. Okay, and you're writing, in case if you do some changes, then you have to write also. So this is read and write. Okay, so yes, bringing to main memory is called read. Okay, bringing to main memory is called read access. This is very costly, because you are dealing with the hard disk to main memory. Bringing something is very costly, right? So this is read access. And writing to the disk, it is called write access. Okay, let me know if that is clear to everyone. So basically, I don't actually. Gate has already asked one question. Let me just tell you. See, we will go to that question little later. Okay. Yeah. But Gate has already asked one question regarding the read and write. See here, this axis, right? Disk axis. So read disk axis means read or write. Okay. So number of disk access, Gate has already asked very recently, and this has very nice number of upvotes, 20,000 views. So Gate has already asked such question. Obviously we will be solving this question, but this has got 20,000 upvotes. Disk access is already mentioned here, right? So you can see disk access, right? So we will be first building the foundation, and then we will be solving these questions. Okay, this is actually, to be very honest, we can do this question now also. I mean, with the we have studied enough to solve this question, but still I will be just building more foundation. Okay, they are just asking contiguous and linked things, so we can still do this question. I mean, there is no extra theory you need to know to solve this question, but obviously the practice, okay, practice you have to do, but theory part is over. I mean, you don't need extra theory to solve this question. Understood? Great. So now what I'm saying here is that in linked list, we are doing the pointer chasing. So for every pointer, you have to basically bring in the main memory. But in the fat, you can bring the entire fat into the main memory. So that's why. So we are still doing the pointer chasing, but can bring the entire fat, into the main memory. So can cheap compared to the dex access. Okay. So that's the only difference between linked and the fat. You can bring complete fat, okay, to the main memory, and then you can do your job, right? So it is not again and again read access. It is just one time bringing, and then you can do your job in the main memory. Understood? It is very popular. We will see. Okay, we will see. Don't worry, you will get to understand. So what they are saying, Windows actually use this fat. Windows decided to by the way, this is slide from Stanford. Windows decided to use store. Windows decided to just store a lookup table of block numbers on the disk. So basically, this is the lookup table or the FAT of the block numbers. Okay. The first thing we do. when booting up the file system is ready, uh, the first thing we do when booting up the file system is read the table into the memory. Okay, so first, I mean, the very first thing that they do is basically bringing this to the memory. Obviously we still need to know the first block of the of every file, right? I mean, we should be maintaining where is the first block, just like this metadata. Okay, we should be knowing where is the first block. These are the you can say start block numbers. Okay, see, let's do this question, and probably you will be, getting to know, getting to understand little more. So they are saying consider this fact table. Okay. So at index 05 is stored, at index 17 is stored. Directory entry means metadata. Okay. Directory means metadata, as I told you. Directory entry says file A starting block is 0. Okay. Now, what is the complete blockchain of file A? So from 0, you will be going to 5. Then from 5, you will be going to 4. From 4, you will be going to 2. From 2, this is end of file. I mean, this is final. This is pointing to null. Okay. So what is the answer here? Let me know. So this is easy, and the answer is A, right? Answer is A. Okay, great. So let me know if there is any doubt till this point. So I hope that you are getting the point, what I'm trying to say. Okay, now let's see this. So they are saying that file view starting block is 2. So from 2, you will be going to 1, and then from 1, this is null. So how many blocks file B is taking? How many blocks file B is taking? Just 2 blocks, right? So answer is A, just 2 blocks. Understood? Great. Now let's move to the next thing, next question. An extent is extent. So basically, this is okay. This is not related to fat. This is related to extent. An extent is extent file. Extent based file system is an extent in an extent based file system. So so what do you understand by this? What is extent? Extent is basically a contiguous block, right? I mean, a continuous group of blocks allocated together. I think B is the answer, right? So B is the answer. So let's just see. Yes, B is the answer. It is contiguous group of blocks, which we call extent. Okay. Let me know if there is any doubt till this point. Great. Now let's just see this question. What they are saying. A linked file allocation system. Okay. So you are not using the fat, you are just using the linked one only. Okay. In the linked one, you have the pointers here. Okay. Pointers in each block. Each block stores 4 KB of the data and 4 bytes of the pointer. So they are saying 4 KB you are storing data and 4 bytes you are storing pointers. Pointer to the next block. A file contain 1000 blocks. What is the total pointer overhead? Okay. So if each block is doing such thing, then what is the total pointer overhead? So you have 1000 blocks. Okay. You have 1000 blocks, and each block is basically containing 4 bytes of pointer. So into 4 bytes of pointer, so you can say you have 4000 bytes of pointer, which is pointer overhead. Okay, so yes, 4000 bytes should be the answer, so which means C is the answer. Okay, is this okay to everyone? Let me know. Great. Now let's go to this question. In this question they are saying a file system uses fat where the each entry is 16 bits. Okay, so this is interesting. So see here, whenever whenever you have the block number or the block pointer number of bits, then you can infer one information from this. See, they are saying each entry, this is fat table. Okay. If each entry, this is 16 bits. Okay. This is 16 bits. What does this mean? By the way, what does this contain? This contain the block number, right? Next block number or the block number. Basically, this contains the block number. If this is 16 bit, if you require 16 bits for the block number, then how many blocks will be there? Yes, overhead basically means extra. Okay. So how many blocks will be there? If you look at 16 bits for the block number, then how many blocks will be there? So you can say 2 power 16 blocks will be there, right? And each block is 512 bytes. So 2 power 16 blocks are there. Just a second, let me go to the next page. Yeah. So 2 power 16 blocks are there. And each block is 2 power 9 bytes, right? 2 power 9 bytes. So this is basically, you can say, the maximum file system size. So this is the total disk size or total, maximum file system size. Okay. So maximum fat entries. How many fat entries will be there? See, see, if they are saying that each entry is 16 bits, right? So number of blocks will be 2 power 16. If 2 power 16 blocks will be there, then 2 power 16 entries will be there, because here each block has one entry, right? So 2 power 16 entries will be there. So you can say 2 power 16 entries, and then if they ask you the total file system size, then one block is of 2 power 9 bytes, and you have 2 power 16 blocks. So 2 power 9 into 16, which is 2 power 25. So B is the answer. Okay. So let me just explain this again if you have any doubt. See, the only key point here is to understand one thing, which is that, let me do one thing. Yeah, let me just copy this. The only point which is important here is to understand is that 16 bit, what is the interpretation of this 16 bits? Okay. If this is 16-bit entry, then can you tell me that how many number of blocks are there? Because if the block number needs the 16 bits, okay, if the block number or the block pointer, the both are the same thing, okay. So you can say if block number or pointer, whatever you like to say, okay, pointer needs 16 bits, then what does this mean? It tells you only one thing. Then total number of blocks, we can always find out total number of blocks from here, which is 2 power 16 blocks. Okay. So if you have 2 power 16 blocks, then you have 2 power 16 entries also. Once you have the 2 power 16, once you know that how many blocks are there, you will get to know the entries, because each block is having one entry here. So how many entries? 2 power 16 entries. And if they want to know what is the total file system size, okay, see, if each block is 512 bytes, okay, each block is 512 bytes, and total you can say there are 2 power 16 blocks, right? So total file system size or total disk size will be 2 power 16 blocks, and each block is 2 power 9 bytes. So 2 power 25 bytes you will be having for the complete disk. Okay. You can say total disk size, right? The complete disk will be of 2 power 25 bytes. Is this understood to everyone? Here, don't worry about the metadata and other things. That's fine. So basically, you have 2 power 25 bytes. Okay. See, you will get to understand, or you will get more practice as we proceed further. right? So the practice will be automatically be done if the as and when we proceed, so don't worry about the practice. Okay. So here, don't worry about the metadata because it's very negligible compared to 2 power 25. So that's why they have not given the metadata size and all. Okay, don't worry about the metadata. Just a simple question to make sure your understanding is clear about the things. Then we will going to the more formulated, more conceptual questions from universities. We will going to the gate questions and all. Okay, great. So so here in this scenario, they are just saying that suppose you have a fat table. Okay, suppose you have fat table which is looking like this, and then there is a directory structure which is just like a metadata. This is directory is nothing but metadata, as I told you. Okay, which will tell you what is the starting block in case of fat. Okay, they are saying that can you traverse file 2 and file 3 in this file system. Okay, let's just try traversing file 2 and file 3. So what is the starting of file 2? File 2, right? Starting of file 2 is 2. Okay, from 2 you will be going to 10. Okay, from 2 you will be going to 10, because from 2 you will be going to 10. From 10 you will be going to 3. From 3 you will be going to 5. From 5 you will be going to end of file. I mean, this is you will not go anywhere basically. So this is file 2, and which is 2 10 3 5, right? So file 2 is basically 2 10 3 5. Okay, so starting is 2, then fat of 2 is 10, fat of 10 is 3, fat of 3 is 5, and fat of 5 is end of file, right? Now similarly you can do for file 3 also. Okay, you can do for file 3 also. So is the traversing okay to everyone, that how this fat is working? Great. Now, now let's do this question which have been asked in GATE 1996. Okay, this is nice question. So what they are saying here, let me just tell you. They are saying you have some disk where disk 0 has the fat. Okay, I mean the first block. I mean the disk block 0 has the fat consisting of 8-bit entry per data block. Okay, so fat entry size tell you something. Okay, I told you the fat entry size tell you something. If it is 8-bit, see, first let me just read the question clearly. So they are saying that you have a disk. Okay, here in this disk, I think here, okay, we will see. This is basically fat. Okay, the first block number 0, block number 1, block number 2, 3, and so on. Okay, this is fat. And block number 1 has the directory with 32-bit entry per file. So basically directory has in case of fat, directory has the starting entry. Okay, I mean starting block number. So so basically each block number here, this is directory, right? This is directory. Okay, so directory is there, and now this is the fat. So directory entry is basically saying that one it is having 32-bit entry per file. Okay, so in one file it is having 32-bit. I mean here it is taking for every file it is having 32-bit. But fat entry is taking 8 bits, 8-bit entry per data block. Okay, so the fat entry is basically 8 bits. So remember directory is metadata, right? Directory is metadata. Now they're asking you that what is the maximum possible number of files possible? Maximum possible number of files and maximum possible file size. Okay, just take 1 or 2 minutes and just see if you can answer this question. So can you first tell me how many blocks will be there? See, fat bits will tell you how many blocks. See, in the metadata, this might be bit bit over, which means in the metadata you might be having something more. Okay, so metadata might be having something more, but using the fat entry is how much? It is 8 bits, right? So which means if you need 8 bits to address the block, can you tell me number of blocks here? It is 2 power 8, right? So you can say 256 blocks will be there. Okay. Let me know if that is fine. And out of those 256 blocks, okay, two blocks are taken by fat and directory. So you can say out of those 256 blocks, two blocks are already taken by fat and directory. So number of empty or usable, whatever you want to say, usable blocks, okay, are basically 256 minus 2, which is 254. Okay, this is basically part B answer. Okay, answer of part B. See, in part B, they are asking you that what is the maximum possible file size in the blocks. I mean, or in other words, basically, a file can take how many blocks at maximum. If at maximum the number of blocks are available with us is 254, so a file can take at maximum 254 blocks, right? Is this okay to everyone? Let me know. Okay. Now, uh, now they are saying that how many maximum files can be there. This is little interesting. See, see, let me just tell you what is happening here. The fat entry is 8 bits, right? So this is fat and this is directory. These are the two different things, right? This is each entry here is 8 bits. Okay. And each entry here is 32 bits. So this is basically containing, okay, this is important. This contains the block number. So from here we get to know number of blocks. Okay, you can say number of blocks are basically 2 power 8, which is 256. Is this fine to everyone? Now, what is the significance of this directory entry? Okay, it can actually tell you number of files. I mean, number of maximum files that you can store. See, number of files. How to get it? Directory is taking just one block. If you notice, they are saying directory is taking one block. Okay, one block is basically 4 KB. Okay, 4 kilobytes, 4 KB. So directory is taking 4 KB size. I mean, the entire size of this directory is given as 4 KB, right? Now, how many? See, one entry will be basically corresponding to one file. So, how many entries can be there? Number of files will be, you can say, number of directory entries. If each entry is taking, this is 4 bytes, right? If each entry is taking 4 bytes, then how many entries can come in this directory? It is basically 4 KB its size divided by 4 bytes, which is 1K, which is 2 power 10. Okay, 2 power 10 entries can come here, which means 2 power 10 files can be stored in this particular file system. Okay, is this fine to everyone? So basically, basically this directory will tell you number of files. Okay, number of files, because number of files are same as number of entries in directory. Okay, let me know if that is fine. Okay, so Viraj is there. Viraj has already got, top rank. So Viraj is saying yes, sir. Okay, great. So let's just see the answer. So each file needs one directory entry of 32 bits, which is basically 4 bytes. So and directory fits in the entire block. So maximum number of files can come is 2 power 10. Okay, and the maximum usable blocks are basically here 254s. Okay, so this is the maximum number of files can come. And obviously, this is limited by the number of blocks. I mean, you can't store, more than 254 files, because anyway you have 254 blocks. But that's fine. In this structure, you have maximum, files can come, which is 2 power 10, but your blocks are even lesser than 2 power 10, which is fine. I mean, this is just a theoretical question. Okay, the exact same question has been asked in gate. I mean, this is gate question only. So the answers are 2 power 10 and 254. Okay, great. So actually, the thing that you should be knowing, that using this fat entry, okay, number of bits here, if it is 8-bit in this fat, then you should be knowing number of blocks. Immediately, you should be telling number of blocks. Okay, this is more important than anything else. Okay, which is 2 power 8. Is this okay to everyone? Okay. See, the question is asking what is the maximum possible number of files? Yes, I mean, you can definitely argue that the maximum could be the 254 only, because it cannot be more than blocks. I think this could be one argument, but it was GATE 1996 question. I don't know if at that time, I don't think challenge was the facility. But if this question being asked nowadays, then probably we can challenge it. Okay. Theoretically, you can store 2 power 10 files, but obviously it is not possible practically here in with this file system, right? Now let's see this question. This question I have taken from IIT Bombay. Okay, let's see what they are saying. So they are saying consider a FAT where a disk is divided into m byte blocks. So block size is given as m bytes. Okay, each block is m bytes, and every FAT entry can store n bit block number. Okay, can you tell me number of blocks? This is 2 power n, right? 2 power n. And block size is m bytes. So what is the maximum size of the disk that can be managed? Can you tell me? 2 power n blocks. Each size is m bytes. So this is maximum disk size, right? So this is 2 power n into m bytes. This is the maximum disk size. Understood? So this question was easy, but you should be knowing the key point here is that if they are saying n bit block number, okay, then it means that 2 power n total blocks. Understood? Now let's solve this question. This question has been asked in GATE 2014. Let's see what they are asking. Just a second. Yeah. Okay. So in this question, they are saying that uh, they're talking about fat only, right? They're talking about fat only. In this question, they are saying that you have fat allocation, I mean, file allocation table, which is fat. Now the total is being used, and the total overhead of each entry in the fat is 4 bytes in size. So fat entry is given to you 4 bytes, right? Given a 100 into 10 to the power 6 bytes disk, total disk size. Here they have given the total disk size. Total disk size is 100 into 10 to the power 6, on which the file system is stored, and the data block size, and block size is also given to you, right? And the block size is also given, which is 10 to the power 3 bytes. The maximum size of the file that can be stored on the disk. Okay, they are asking maximum file size. See, let me just give you a little bit of hint and then you can solve this question. Okay, just take 1 minute and then solve this question. See here, I mean not the hint, but just let me just reiterate this question. They are saying this total disk size. Let's suppose this is disk. The total size is given to you. Here somewhere you are storing fat. Okay, and then this is your I mean here you will be storing your files. Suppose you want to store only one file, then it can span over all the remaining blocks. So basically you can say this is maximum file you can store, maximum file size. I mean they're asking you this. Basically they're asking you fat size, I mean the how many blocks this fat will be taking, fat size, and then you can subtract from the disk, right? So if the fat entry is 4 bytes, then can you tell me how many bits it is? 32 bits. From here, can you tell me number of blocks? Can you tell me number of blocks? Let me write it here. Okay, let me write the solution here. See, number of blocks, can you tell me? 2 power 32, right? Number of entries in fat, can you tell me? Entries in fat is also 2 power 32. And each entry size is 4 bytes. So can you tell me fat size? 2 power 32 into 4 bytes, which is basically 2 power 34 bytes. Is this okay to everyone? Let me know. See here, by the way, this this 4 bytes might not be the block number, right? So they are saying that that each entry in the fat is 4 bytes, but they are not saying the block number. See, earlier they have said the block number directly. See, in the earlier question, they are saying, for example, n bit block number, right? But here it might not be directly block number. So first you have to find out number of blocks, and then number of which will be same as number of fat entries, and then you have to calculate the fat size. Okay. So how many blocks are there? See, the total disk size is given to you and the block size is given to you, right? Can you find out the number of blocks? So the total disk size and from the block size, right? You can find out the number of blocks. Okay. I mean these 4 bytes. See, this was the mistake that people can do. That the 4 bytes here are not the block number. I mean it could be the block number and some more things. Okay. This because this is just a metadata. Until and unless they specify that these are the block number. I mean these are the bits that are taken by the block number. You cannot assume this, right? So number of blocks will be total disk size divided by block size. I think both are given to us. Okay. So from here we can find out number of blocks, which is 100 into 10 to the power 6 divided by 10 to the power 3, which is 10 to the power 5. So these many blocks are there. So if you know number of the blocks, right? If you know number of blocks, then don't you can't you calculate fat size? What will the fat size? Number of entries in the fat will be same as number of blocks. So the fat size will be, see, let me go to the next page. So they are saying that block size is 10 is power 3 bytes. Disk size, right? Disk size is 100 into 10 is power 6 bytes. Number of blocks you can calculate, which are 100 into 10 is power 6 divided by 10 is power 3, which is 10 is power 5. So fat size will be number of entries here into size of each entry is 4 bytes, right? 4 bytes. Okay. Now what is the remaining size? Can you tell me what is the remaining size? See here, we need to know from the total disk we can subtract the fat size to get the remaining size, right? So what is this remaining size? This will be total size. This will be total is 100 into 10 to the power 6 minus minus 10 is power 5 into 4, right? So 10 is power 5 you can take common. So it will be 100 into 10 minus 4 into 10 is power 5, right? So this is the remaining size, which will be I think 996 into 10 is power 5. Okay. So 996 into 10 is power 5 is remaining size. Now, actually, they are saying that you divide, I mean, you divide your answer by 10 is power 6. I mean, they are asking in the unit of 10 is power 6, which means you divide your answer by 10 is power 6. So, so basically, this size is coming out to be 996 into 10 is power 5 bytes, but they're asking you to divide by 10 is power 6. Then it will be 99.6, right? 99.6. So 99.6 MB is correct answer in unit of 10 to the power 6. So basically these questions are just kind of aptitude questions only. I mean, given the information you can solve it, right? Okay, so most of you have done the correct calculation. Great. Now let's just move to the next allocation strategy, which is indexed allocation, right? So basically, if you remember that we have different allocation strategies. So we have seen contiguous, right? We have seen linked, we have seen extend, we have seen fat. Now we are here, right? Now we are here. Now we will see index based. Okay. Let's just see what is the index based allocation strategy. So it is just saying one simple thing. In the fat, we have table for entire disk, but here we have only for file. Okay. In fact, we do pointer chasing. I mean, you go from here to here, here to here. Here you have direct pointers. I mean, here you don't have no need for pointer chasing. Okay. For each file, there is separate metadata which is called inode. No need for pointer chasing. You can say for each file, there is separate metadata which is called inode. Here, inode means index node. Okay. So you can say for each file, there is separate metadata, data structures basically. So it is just data structure, right? I mean, practically this inode is just struct in C programming. Okay, so called inode. Practically it is just struct. Okay, full form is index node, right? So it actually has all the pointers. It actually has all the pointers directly. So here you don't have to do any pointer chasing. Which means if you want to go, let's suppose, to fourth block of the file, let's suppose, I say that some file, okay, suppose I say that some file has been divided into four blocks or three blocks or whatever, right? Suppose, there is some file, okay, this file has been divided, let's suppose, into four blocks. Now now you can say that if you want to go, see this block in the disk, this block can be stored anywhere, by the way, right? I mean, if you talk about the disk, then you can store this block anywhere. Okay, this is file A, and this is block 0 of file A, and then you can store it anywhere, right? You can store this anywhere, you can store this anywhere, right? You can store this anywhere, and so on, right? I mean, you can store these things anywhere. Now, inode will be directly telling you. Suppose you want to go to the block number 3. Okay, I mean, if you're starting from 0, then let's suppose you want to go to the fourth block, which is block number 3. I mean, fourth block is basically, I mean, counting will start obviously from 1. I mean, if you want to count something, that has to be started from 1. But the block number is 3, right? Okay. So, if you want to go to the fourth block, you can directly go to the fourth entry, 1, 2, 3, 4. Okay. You don't have to do anything. You just have to write inode. Okay, inode something like this. Okay, inode 4, inode 3. Okay, then you can directly get this, directly get, okay, directly get this without any pointer chasing. Is this okay to everyone? Great. So basically this is inode where you can directly get these pointers without any pointer chasing. No need, or in other words, I have already written that, so let me write in other words. For any block of any file, go to inode of that file, then directly get the block address, then directly go to the desired block without pointer chasing, right? Without pointer chasing. Is this fine to everyone? Let me know. Okay. I mean, you can directly go to, let's suppose you want to go to third block, you can directly go to this entry and then third block. And then if you want to go to second block, directly go to this entry and second block. This is called inode. Now, for example, like this file A will be, the file A inode is like this. Okay, it will be having its pointer. File B inode will be having its own pointer. Okay, like this. Now, as I told you that we are going to see the variation of this, right? Which is called multi-label inode or multi-label indexed. Okay, so the next topic is multi-label index. I mean multi-label inode. Multi-level index node, which is also called as inode. I mean, inode is only there, but you can have multiple levels. What does this mean? Let me just tell you. See, by the way, this is Stanford slide, and this is very funny. What they are saying, that there's a life tip. If a design scheme uses word multi-level, it's usually the right idea. Okay, so for example, multi-level paging. Okay, like that. This works. They are very funny. They are saying this works for CS 111. This might be their course name. Not so much in real life. For example, multi-level marketing. Okay, MLM. So I don't know if you have got this joke or not, but yes, it was funny to me. So that's why I have kept it. Okay, so usually the multi-level things, they are saying it is correct idea unless it is multi-level marketing. Okay. So multi-level paging is nice idea and so on. Great. So let's just see what is this multi-level inode or multi-level index. See, earlier I was directly pointing to the data blocks, but now they say that you may be having something which points to which points to a block. This is just a block only, okay, and which is having three pointers, or based on the size, it will be having multiple pointers, okay. So basically, earlier, this is earlier. You can say this is the earlier story, okay. This is earlier we were only having this. Now here, these pointers can point to something which can point to the blocks. Okay, this is called singly indirect, and doubly indirect means this can point to something which can point to something which can finally point to the blocks. Okay, I will show you. See in the direct addressing. See, this is like direct. Okay, this is called direct. This is direct only. Okay, this is the direct. I mean, these are the direct pointers. You can say these are the direct pointers only. Direct pointers, which are pointing to the blocks. Okay, these are the direct pointers which are pointing to the blocks. Now, in direct addressing the block, let's suppose the block size is 512 bytes. Okay, payload size, or the file size. So basically, let's suppose this is the 512 bytes. Now you can have indirect pointers also. Okay, for example, you can have singly indirect. Like for example, in this diagram, can you tell me which pointer is singly indirect? In this diagram, can you tell me which pointer is singly indirect? This pointer, right? This pointer is basically pointing to some block, okay, which is finally pointing to something. So this is called singly indirect. Singly indirect means this is basically pointing to some block, okay, which points to multiple blocks. Okay, so this will be clear. See here. So it is pointing to multiple blocks. So basically, singly indirect pointer means something is pointing here and this is pointing to multiple blocks. This is singly indirect pointer. Okay. Similarly, okay, before I go to the multiple more, so let's just do a some aptitude here so that you get to understand this more and so that you can solve gate questions. Suppose, let me ask you a question. Suppose that block has, block size is 512 bytes. I mean, basically there is a single indirect pointer which is pointing to this, and this block size is 512 bytes. Okay, the total size of this block is 512. Earlier this was the real data, but now this is not the real data. See, earlier if it is a direct, okay, now there is a direct pointer which is pointing here, right? So this is the real data. Okay, this is real data. And what is the size of this? This size is also, obviously it is also a block, so this is also 512 bytes. Okay, this was the real data. But now something is pointing here, and let's just assume that block size is 512 bytes. So basically this size is 512 bytes. Can you tell me the number of pointers it can have? If each block pointer size is 2 bytes, okay, then number of pointers it can has. So basically what I'm saying, I'm asking that how many number of pointers it will be having. This is important, okay? Number of pointers pointers singly indirect has, equal to block size, okay, and one pointer size, which means two 256, right? 256 pointers it can have. Is this okay to everyone? So it has 256 pointers. So it means it can point to. What does this mean? If it is having 256 pointers or 256 block numbers, then it can point to it 256 blocks. Okay. So earlier it was just one block, okay, I mean just one data, but now it can point to 256 different. Fine. So let me just ask you a simple question. Let's suppose there is one inode. Okay. It just has, let's suppose this is the inode. It just has, let's suppose two, for simplicity, I'm just asking you two pointers. This is direct pointer. This is single label pointer, single level in direction. Okay. And block size is anyway 512 bytes. And block number is 2 bytes. Okay. Block number is 2 bytes. Tell me size of this file. Okay. Whoever is having this inode, size of this file. Okay, you can say maximum size, I mean maximum size of this file. See, maximum it can have one block here, right? So one block it can have from direct, right? So it can have, you can say one block here. This will be one block, right? And it is pointing to some block which will be having 256 pointers, right? So it can point to 256 different blocks. So 256 blocks here. Okay. So 1 plus 256, which is you can say 257 blocks, can at maximum the file can take 256 7 blocks. Are you getting my point? See, this can hold one block, right? I mean, this will be pointing to one block, and this can effectively point to 256 more blocks. I mean, it will be pointing to some block which will be anyway having only pointers, and how many pointers? 256 pointers. So that's why 257 total blocks I can point to using this inode. So maximum file that I can store using this inode is 257 blocks. Okay. So don't worry, you will get to understand. Let me go step by step. See here, how many bytes our singly, okay, so basically direct block can refer to. How many bytes it can refer to? So basically it is referring to 256 blocks. Okay, so you can say it is referring to 256 blocks, and each block size is 512 bytes, right? In terms of the bytes, it can refer to these many bytes. I mean, just this block only. Okay, just a single block. So you can say 256 into block size, which is this. Is this fine to everyone? Let me know. Okay, are you finding it too difficult? See, it is just saying that, okay, it is actually, you will be finding it very handy once you do little bit of practice with me, and we will be making sure that everything is crystal clear to you. Okay, so we will just make sure today that everything is crystal clear to you. Okay, great. So, so basically, I'm saying here is that this particular singly indirect will be pointing to 256 blocks, and in terms of the bytes, it will be pointing to 256 into the block size, whatever, right? So 256 into 512 bytes. In terms of bytes, this will be the answer. Okay, just a second. It is basically saving, so I cannot proceed once it is until and unless this is done. Okay, let me do cancel. I will do it later. So, so basically, suppose you have doubly indirect. Okay. Now it will also point to 256 blocks. And now I'm choosing that, okay, each of this block will again point to 256 blocks. Okay. So how many total blocks this will point to? Can you tell me? Total blocks, that total data blocks that this will point to. See, it is just like a tree. Okay. So it is having 256 into 256 blocks, right? that this can point to, because this is pointing to 256 blocks and each is pointing to 256 blocks. Okay, if it is doubly indirect, is this fine to everyone? So 256 blocks into 256 blocks. Okay. Yeah, you can use the formula, but we will just build up the formula. So basically, basically, let's do some question and then you will get to understand this very clearly, right? It's easy only, but they have asked it multiple times, so that's why it is important also. Consider file system with 512 byte blocks. So block size is given to you. Okay. Assume an inode of file holds pointers to n direct data blocks. So basically they are saying direct pointers. Okay. So direct are n. Okay. Direct are n and a pointer to a single indirect block. So single indirect is just one. Okay. Further, assume that single indirect block can hold pointers to m other data blocks. So they have given you that it can hold pointers to m blocks only. Okay. So it can hold pointers to m blocks. Okay. What is the maximum file size that can be supported by this design? See, you have only two. One is direct. Okay. Um, so you can say sorry, and direct, right? And direct. So basically n blocks because of the directs. So n blocks because of the direct pointers, right? So there are n pointers and direct pointers you have, and only one indirect you have. Okay, but this can point to, they've given you directly, this can point to m blocks. So how many total blocks? Easy question, n plus n blocks, right? Okay. So basically m plus n blocks, and if block size is 512 bytes, then you can say n plus m into 512. Now let's solve this question. What they are saying is that consider file system with 2048 bytes block. Okay. So the block size is given to you. Let me write here 2048 bytes and a 32-bit disk. So what does this mean? 32-bit disk. It means that basically the block number is 32-bit, right? So the number of blocks is 2 power 32. Okay, 32-bit disk actually mean the number of the block number is 32-bit, and a file block point 32-bit disk and a file block pointers. Each file has 12 direct pointers. Okay. So before I go to that, can you tell me how large the disk can be? If the number of blocks are given to you and block size is given to you, you can just multiply, right? These two. So basically it is 2 power 32 into this is 2 power 11. Okay. This is 2 power 43 blocks, 43 bytes. Okay. These are this is the maximum disk size. Let me just check. So 2 power 43 bytes, right? Is this okay to everyone? Which is basically same as 8 into 2 power 40 bytes, which is 8 terabytes. Okay, 8 TB. So basically, this 32-bit disk means that you have block pointer is 32 bits. Now, let's solve the next question. For that, I need this inode structure. So basically, they are saying 12 direct pointers you have. Okay, so 12 blocks anyway you have. One singly indirect. Let me first tell you that how many pointers any block can have. So pointers in a pointers in a block. So you can say that block size upon pointer size, right? Pointer size is basically 32-bit. So it is 2 power 11 divided by 2 power 5, which is 2 power 6, right? So 2 power 6, you can say the pointers you will be having. Okay, 2 power 6 pointers you will be having. So now let's now solve this question. So you have 2 power 6 pointers, okay, in any block. So 12 direct pointers, so 12 block directly. One single indirect, which means one block which will point to many things. So basically it will hold 2 power 6, right? 2 power 6 blocks, right? Pointers, or 2 power 6 pointers it will hold, right? So basically if it is one single indirect, so it will be holding 2 power 6. If these are two single indirect, then 2 into 2 power 6, something like this, right? One doubly indirect, so which means 2 power 6 into 2 power 6. Okay, it will keep on multiplying. One triple indirect, 2 power 6 into 2 power 6 into 2 power 6. These many blocks will be pointed by one double indirect. If these are, let's suppose, 5 double indirect, then 5 into something. Okay. So these many blocks, this file can span to. So these many blocks. In terms of the bytes, if they are asking, then you can multiply by 5 and 2. But yeah, these many blocks. Okay. So it will be 12 plus 2 power 6 plus 2 power 6 into 2 power 6 plus 2 power 6 into 2 power 6 into 2 power 6. Then you can multiply by the block size if you want to. Okay. So basically, these questions are easy only. Don't worry. You just have to find out the pointers in one block. Okay. And then for singly indirect, directly you can write these many pointers. If this is doubly indirect, then you can multiply one more time. If it's triply indirect, you can multiply one more time. Okay. Okay. So probably we can directly solve one gate question here, which has been asked in GATE 2019, and there are many other questions that they ask. Okay, so GATE 2019, GATE 2004, and I mean I think there are 2 3 questions just based on the simple concept. Let's just see. I node, they are saying index node of Unix file system has 12 direct. Okay, first tell me what is the block size. Block size is given as 4 KB, right? Disk address has 32-bit longs. Is this same as oh my god. Is the same as the previous question? Yes. I think the block size. Okay, the block size here 2 power 2, 2 power 12. And here it is 2 power 11, right? Yeah, block size is little bit different. Otherwise it is same. Okay, anyway. So basically, this is 2 power 12 bytes. Otherwise, this question is same as, this university question. I've taken this question from some university. Let me just tell you. I think this was Cornell University question. So I have taken this question from, yeah, Cornell University, and this is the same, almost same question that they have asked, right? Okay, just the block size is difference. Otherwise, the same question only. In GATE 2019, they have asked the same question. So the block size is this. Then how many number of pointers you can have in one block? Block size divided by the pointer size. Pointer is 32-bit long, 2 power 5, right? So 2 power 7. 2 power 7 pointers you can have. Now it is easy, right? So they are saying that you have 12 direct, so it is 12, right? Direct plus one singly indirect, so 2 power 7, plus one doubly indirect, so 2 power 7 into 2 power 7, right? These many blocks. So they are asking in GB. So basically, you first convert into the bytes, so which is 2 power 12 bytes, and for the GB you can divide by 2 power 2 power 20, right? Okay. So you can solve this question. So see here, this is 12 into 4 kV plus something like this, which is coming out to be 4.4 GB, approximately 4 GB. Actually, it will be almost same as the last thing. Okay, I mean, generally it is almost same as the last thing. So you can say, sorry, you need to divide by 2 power 30. Okay, you need to divide with 2 power 30 for the GB. 2 power 30. I mean, 2 power 10 is KB and then MB and then GB. So basically, I mean, generally these things are very small compared to this. So basically, it is nothing but 2 power 20 into 2 power 2 into 2 power 10 bytes divided by, which is divided 2 power 30, which is just as 4. Okay, 4 GB. If it is triple indirect or something, then generally these are very small compared to this. Okay, generally these are very small. So 4 GB is the correct answer. Easy question, but yeah, I hope you got to understand. Now let's see this question. This is almost a similar kind of question. Okay, block size is given as this. Node has 10 direct pointers, so block size is given as 1024 bytes. 10 direct. Okay, first let me know the number of blocks so that I can basically know the pointers. Okay, 128 blocks. So number of blocks are basically 2 power 7, which means that's 7 bits. Okay, which means 7 bit is a, you can say, the pointer size. Okay, so you can say 7 bits pointer size, because number of blocks are 128. Okay, since they're asking approximately, so you can approximate it to the nearest, which means 8 bits, right? So you can say 1 byte. Okay, so which is 1 byte, because they are asking approximately. Now you can you can do one thing. You can find out number of pointers in a single block. This will be 2 power 10 divided by 1, which is 2 power 10 pointers, right? So it will be having 2 power 10 pointers in single block. Now you can solve the remaining question. Okay, so basically let me just do it. So they are saying the 10 direct, so 10 direct plus direct block addresses and 3 additional addresses, 1 for singly indirect, only one, right? So 2 power, how much was that? 2 power 10. 2 power 10 singly, 1 for double, 2 power 10 into 2 power 10, plus 1 for triple. Okay, 2 power 10 into 2 power 10 into 2 power 10, right? So generally this will dominate, right? So basically these many blocks are there, and in terms of the bytes, you can multiply by 2 power 10, right? So these many bytes are there. So you can say that 2 power 30 is this. So 2 power 30 means basically you can say 2 power. Have I missed something? No, this is live. Okay, so someone is asking this live or previously recorded. No, this is live. So let's just see the answer. So this is pointer capacity per block is 2 power 7. Let me just see why. Okay, they've directly given that each block can contain the addresses for 128 blocks. Okay, so they are directly saying that okay, each block can contain addresses for 127. So which means that 128, which means that each block is having 128 addresses. Okay, so basically you can say number of, directly they have given to you that number of pointers in one block is 2 power 7. I mean, they have directly given to you this. Okay. Number of block and content addresses for 128. They are directly given, so you don't have to calculate because you can't even calculate because they have directly given. Okay. So earlier I thought that this is these are the number of blocks, but anyway, so this is not the number of blocks. It is okay. It is basically number of pointers in a single block. Now these many, if these many pointers this can store, then 10 plus 2 power 7 plus 2 power 7 into 2 power 7 plus 2 power 7 into 2 power 7 into 2 power 7, right? So these many blocks it will be pointing, something like this, right? So generally, as I told you, the last one will dominate. Okay. So 2 power 21 blocks are reachable, right? So which means 2 power 21 into 10, 2 power 10 because this is the block size. Okay. So 2 power 31 bytes, which is same as 2 GB. Is this okay to everyone? Let me know. Okay. Now, if that is fine, then we will be doing few more gate questions, and then we will be wrapping up this. So let's just do few more gate questions. Let's do this Berkeley University question. Okay, before we move to few before we uh, move to the few more gate questions. So let's see this Berkeley University question. What they are saying: in a FAT file system, each file's blockchain is recorded in a table. During the random access to the nth block of the file, how is the block located? So basically, you want to directly access the nth block. Okay. So how many disk access are typically needed? So as I told you, there will be two disk access. Why? Because one for the fat, and using the fat you will get to know the nth block address, and then one for that, right? So this will be two. So B is the answer. I mean, one for the fat, and using the once you bring the fat to the main memory, then using that you will get to know the pointer to nth block, pointer to nth block. Okay, and then from this you will be basically loading or reading basically whatever you want to say nth block. Okay, nth block. So that's why this is one read and this is another read. Okay. Now let's see this question, which is actually a little more interesting question. What they are saying: a file system may organize the blocks of a file using one of these three strategies: contiguous allocation, linked allocation, or the index allocation. So basically, they are either using contiguous, linked, or indexed. For contiguous and linked, the system already knows the first data block of the file. I mean, the metadata obviously for the contiguous and linked. So you need to know the first where is the first block. So the system already knows. Suppose for index, the system already know the index blocks, which is the inode. Okay. You want to bring 10th data block file into the memory. Let R be the number of disk blocks must be read in this process. So basically, you want 10th data block, okay, of some file. So how many disk access you will need for the contiguous? See, the contiguous will be stored like this. This is complete disk. Okay. Any contiguous file will be stored like this. If you already know where is this first, okay, can you directly tell me where is this 10? Where is the 10th block? Can you tell me directly? Yes, we can directly tell because in the contiguous we can just have the offset. Like we know that okay, this is after the 10th file or something, right? So we can directly tell for sure. So which means that we can directly know that where is this, and then we can bring this into the main memory, right? So only one access to bring in main memory. Why? Because I know the pointer directly. Okay, I know the pointer directly. Is this fine to everyone? Now, what if this is linked? Okay, suppose if it is linked, then I only know the pointer to the first. Okay, suppose if it is linked, I know this pointer, and suppose I want to go to the third block, then I will bring this to main memory. I will read this, then I will get to know, okay, where is this, right? Then I will bring this, and then I will get to know where is this, and then I will bring this, and ultimately I will read the data of this. So basically, if I want to access the data of the third, then I have to bring this into the main memory because I want to read this pointer. I have to bring this into the main memory because I want to read this pointer. I have to read this in the bring this in the main memory because I want to read the data from this, right? Because if this is third block, then I need three read. I mean, I need to bring three times the first this, then using this I will fetch this, then using this I will finally fetch this, right? So basically you can say three read access, three, right? For three, if these are the 10 blocks, then you can say 10 read access for the linked. Okay, so for the linked 10, and if it is inode, in that case you can bring the complete inode, right? Okay, if it is inode, system already knows the index block of a file. So you have to bring the inode, and using the inode, you will directly get the pointer, and then you can basically bring that, right? So basically, if it is inode, then just like a fat, okay, just like a fat, I mean, you have to bring this inode first. So one read for inode and one read for the 10th block. So two. For inode, this is two. For contiguous, it was one, because you can directly know that where this is present. Okay. For linked, it is 10. So for contiguous, it is 1. For linked, it is 10. For inode, this is 2. So what is the answer? A is the correct answer, right? So answer is A. Is this okay to everyone that how we are solving this question? Let me know. Okay, great. Now, let's do one thing. There are a couple of more, gate questions that I wanted to solve. So let's just solve these questions tomorrow, and I will be also solving. Okay, I will be also solving all the quiz questions. So basically, I have given one quiz, and I will be solving all of these quiz questions also. Okay. So these are the 15 questions that I have given in the quiz. So all these 15 questions I will be solving along with the all gate questions. Okay. And there is one nice gate question that they've asked. If you want, you can try it for the next video. Okay. Try it before next session. We will be having it tomorrow only. Understood? Okay. So thank you everyone. If you have understood something in the file system, then let's do one thing. You can just like this, or you can just comment it out. If you have really liked the session, you can just let me know if there is anything that we need to do. Okay. So you can just comment out your views. Okay. If you like the session, just let me know. Thank you everyone.